Hi, I'm Bill Lauder. I'm the CTO at DeepHealth, and I'll be talking about our efforts in building AI-optimized synthetic 2D mammograms that achieve high levels of performance in dense breasts. Here are our disclosures. Overall, the goal of this work is to build an AI system for DBT. In doing so, we want to take advantage of DBT's benefits, specifically its benefit in mitigating tissue superposition. We'd also like to take advantage of transfer learning, a common technique in machine learning where you use a model pre-trained on one task to help you on a new task. Here we'd like to leverage 2D data and models for transfer learning to DBT. The core challenge, however, is the large data size of DBT. With DBT, the amount of data can be 100 times more than FFDM. This amount of data isn't just challenging for the human cognitive system, but also for AI algorithms. For one, it's computationally challenging. Even the best GPUs struggle with the amount of memory required for DBT, and even 2D models can take a week to train, so scaling this naively to DBT could take months. But most significantly, the large data size of DBT makes it highly susceptible to overfitting, where an AI model may memorize spurious features in the data that aren't actually predictive of cancer. This overfitting is caused by the needle in the haystack nature of DBT, where subtle malignant features may only be visible in a small proportion of the overall volume of pixels. Obtaining detailed annotations can help with overfitting, but annotations themselves can also be noisy and hard to scale. So how can we go about this? Well, one thing all radiologists know is that 2D and 3D mammography are complementary, and it turns out that this is actually the case for AI too. Synthetic 2D images, for instance, are a way of collapsing the DBT volume into a single 2D image, and this approach could be amenable to AI. Of course, in creating a synthetic 2D image, you necessarily lose a lot of information. So the question becomes, can you create a synthetic that gets rid of noise but retains the important information? There's an infinite number of ways you could imagine creating a synthetic. Ultimately, the problem amounts to specifying an algorithm that takes a DBT stack as input and outputs a synthetic 2D image. For instance, you could imagine using a maximum intensity projection or a MIP-based approach. Once we have the synthetic, then we can train another algorithm that takes the synthetic 2D as input and classifies whether cancer is present. So with this approach, we get two useful things: the synthetic creation algorithm and a full DBT classifier. We've pursued this approach and have created our own custom synthetics, which we call D-views. So the approach consists of an algorithm that generates the D-views, followed by an algorithm that classifies the D-views for the presence of cancer. In this talk, I will primarily focus on the D-view generating algorithm, but more details regarding the D-view classifying algorithm can be found in our other SBI abstracts, which are cited later. For this classifier, we use the same model architecture that we use for FFDM. So focusing on the generating algorithm, we developed an approach that uses a pre-trained AI model to sift through all of the DBT slices, and at each spatial location, the AI model finds the region that appears the most suspicious out of all the planes. The most suspicious regions at each location are then collapsed and merged using additional image processing techniques into an optimized 2D synthetic. Overall, you can think of this method like a MIP, but instead of taking a maximum over pixel intensity, it's taking a maximum over cancer suspicion as deemed by an AI model. And instead of operating at a pixel level, it's operating at a region of interest level. In this sense, the D-view synthetics are optimized for cancer detection and to particularly take advantage of the tissue superposition benefits of DBT. So let's see how well it works. In designing a study to test its performance, there are three main steps. First, we need to train the AI model used in the D-view generating algorithm. Then we need to train the D-view classifier. And finally, we want to evaluate the performance of this classifier. For each of these steps, we use a different dataset to best test generalizability. The first dataset consists of 2D mammograms to train the D-view algorithm. Then we use a DBT dataset to train the D-view classifier. And finally, we test on a separate DBT dataset consisting of 1,000 studies with 100 cancers, where non-cancers are either negative BI-RADS or confirmed benigns. Again, there was no overlap in the data sources across the 3 datasets. Here are the results. We measure AUC for an ROC curve as well as the sensitivity at the BCSC average specificity. We would expect some difference in performance between dense and non-dense breasts, but we find that our approach achieves high levels of performance in both types with an AUC of 0.96 on non-dense breasts and an AUC of 0.94 on dense breasts. Thus, the performance is high in both dense and non-dense breasts, and the difference in performance is also relatively small. Finally, here are some examples. In this first example, there's a posterior malignant mass for which you can see the spiculations much better on the D view on the right compared to the default synthetic on the left, where the spiculations are obscured by overlapping tissue. The classifier model does indeed give the D view a higher malignancy score. Here's another example where you can see the spiculations much clearer in the D view. So in summary, we developed a novel algorithm that collapses suspicious information across the DBT volume into an optimized image. Within an end-to-end AI pipeline, the approach performs well on both dense and non-dense breasts. We envision that our approach may additionally prove to be useful as an aid for interpreting radiologists. Finally, we'd like to thank some of our funding sources, and please check out our other abstracts as listed below. Thank you.